functions. Over there. There we go. All right. And this is what your circuit training this week is over. By the way, circuit training, because it's a no homework weekend, I'm not making due Tuesday. I'm making it due Wednesday, just so you have that extra day if you want. I don't want to make anything due the day you come back from that long weekend. Okay. All right. Inverse functions. Okay. So we talked about a few sections ago what makes something a function. A function is when each x has one y. Okay. Then, and we also did like a vertical line test with that. If you remember, there were a few different ways we could figure out if something was a function. There's also something called a one-to-one function. So if something is a function, it could also be a one-to-one function. This is like a special case of a function. Each x has one y, but also it works the other way. Each y has one x. And it's important to know if something's a one-to-one function or not, because that means we can calculate an inverse. We say that something is invertible if we can calculate that inverse. All right, so we're going to look at these correspondence diagrams first, and we're going to ask ourselves two questions. Question number one is it a function? Does each x have one y? And then if it's a function, we're going to ask the next question. Does each y have one x? Okay, so for the first one, does each x have one y in that diagram on the left? Does each x have one y? Yes or no? Yeah. Yes? You sure? No? Where is it a no at? Yeah, x2 makes it not a function. So because it's not a function, it is obviously not a one-to-one function then either. So that's really the only question we have to ask ourselves. Okay, so the one in the middle, is it a function? Does each x have one y that it goes to? Yes, it's a function. Okay, now let's look the other way. Does each y have one x? No, this guy's a problem. That one y goes to two different x's. So it's a function, but it's not one-to-one, okay? Which means for us, for this section, and all the rest of math, when you do inverses, you will not be able to calculate the inverse, okay? Last one, does each x have one y? Yes. Does each y have one x? Yes. So this is what a one-to-one function looks like when we're looking at coordinates anyway, okay? Questions so far? All right. So how you tell if a graph represents a one-to-one function, which is, remember, our easiest way to do things. Hey, sir. You're good. Another class. Okay. All right. So if we want to tell if something's a function, we just do the vertical line test. If we want to tell if something is a one-to-one function, we do the horizontal line test, and that tests for both things, okay? So for example, for this first graph on the left, does it pass the vertical line test? Yes, it's a function. Would it pass a horizontal line test? No, it would not. Okay, so something like here, okay, if I drag that horizontal line up and down on my graph, it's going to touch multiple parts of the graph at a time. So that represents one y that has a bunch of different x values that go with it. That's the visual representation of what we're just looking at, that correspondence diagram. So it's a function, this one, but it's not one-to-one. Okay. What about the parabola? Is it a function? Does it pass the vertical line test? Vertical line test? Yes. Does it pass the horizontal line test? No. Okay, now what if I get rid of that half and I just say only use the right side of the parabola? Now does it pass the horizontal line test? Yes. So you're going to see in a lot of our equations things that look like this at the end of the equation. It's a little kind of like indicator that says, hey, the whole thing isn't going to pass the horizontal line test, but if I only look to the right side of 0, it will pass the horizontal line test, so that allows us to calculate the inverse. So when you see stuff like that at the end of an equation, it's just allowing us to be able to calculate the inverse, okay? It's just restricting the domain. All right, what about the last one? This is a graph of our reciprocal function, one of our parent functions. Does it pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. So this is an example of a one-to-one function if we're looking at the graph. Okay? All right, so now let's say we know something is a one-to-one function and we want to be able to calculate the inverse. What is an inverse? An inverse is when we take all of the x's and y's and we swap them. Okay, so literally our coordinates are switched. If I have the coordinate 3, 4, the inverse of that coordinate is 4, 3. Okay, and we're going to see what that looks like with points, graphically, and when we're talking about equations, we are literally taking the x's and y's and we are switching the x and the y, and that gives us an inverse function. Okay, so one of the first things that you need to know is inverse notation. It's going to look like a -1 power. Often it's going to be written with function notation, so there will be a parentheses after it. There's a big difference between if you put the -1 after the name of the function here, or if you put it after the parentheses. This -1, if I write it at the very end like that, means a negative exponent. Move something to the denominator. It's very different. If you put it after the name, it's more of a label, just saying, hey, this is the inverse. Also, I would maybe like circle this or underline this. This is a nice little notation to tell you, like, hey, if you're looking at an inverse, what's in the parentheses, it's switched now, is a y, and what's outside the parentheses is an x. Okay, that's a big idea. So if we're looking at like this guy down here, the first part I see is just a normal f. Doesn't have my inverse notation, which means what's inside the parentheses is an x and what's outside the parentheses is a y. But now I'm looking at the inverse. Okay, so what's inside the parentheses? A y. And the question is, what x goes with that y? Well, we should already know that, right? Because we have the inverse of it. We have function f. The answer is -3. Problems like this are very quick. They're just asking you to recognize, like, hey, I know what an inverse does. I know it switches the x and the y. So if I have an x and y that go together, I know they're just going to be switched in that inverse notation. Okay, so don't overthink problems like this when you see them. All right. Let's say we want to graph an inverse. It is literally as easy as taking your coordinates and flipping them. That's all you got to do. So if I have the point 8, 8, and I swap the x and y coordinates, where does it end up? 8, 8 switched is still 8, 8. Okay? 3, 6 will end up where? 6, 3. -1, -1 will end up where? Same spot. Okay. And then -5, -2 will end up at -2, -5. Down there. If I connect those points, what you see in blue on mine is the graph of f inverse. Okay, and the original guy there is the graph of f. Do you guys see how that's a reflection in this picture? Can you see that? Maybe I could draw the reflection line in here. The reflection line is just this diagonal line that goes through the origin. Do you see it? The mirror image there? That line is one of our parent functions. It's our identity function, y equals x. So this is actually going to be a great way for us to check that we have inverses. We can graph both of them on the same graph and see that we have this reflection over a line. So like if you're doing math Excel questions and you have to look at a picture quickly and name which one's the inverse, this is what you're looking for. You're looking for the one that has that reflection over that diagonal line, and that can make it easy to identify it. Okay. Questions on that? All right, moving on. Okay, so I mentioned this a little bit yesterday. If you remember yesterday, the one problem you guys did with like the square root and the squared, we did composition two ways. We plugged g into f, plugged f into g, and we got out x both times. If when you do composition both ways and you get out x both times, that is a proof that you have inverses. If you compose in either direction and you do not get x, you get something else like x squared or 3x or x plus 4, they are not inverses. Okay, so you will be asked, like on quizzes and tests, to verify, remember that means like prove, okay, that the following are inverses of each other. And it might say using composition, because using composition is how we prove that. Okay, so what we're going to do is we're going to plug the functions into each other. It does not matter which one you do first because you will be doing both of them, ideally, hopefully. Okay. When I see notation that looks like this, what does that mean? Plug what into what? G into F. Okay. So if I plug G into F, practiced this yesterday, I'm going to take function G and I'm going to put it into function F anywhere I see a variable. So that looks like 3 parentheses. Take the x out, put x minus 1 over 3 in its place, plus 1. Blair, do you have this paper? No? Oh, I thought that was one on your desk. Sorry. Okay. Let's simplify. What can I do first here? I could. I don't have to here, though. That 3's over 1. I have a 3 on top and I have a 3 on the bottom. What's going to happen with my 3's? They're going to cancel. X minus 1 plus 1. And what am I left with? X. Good. Okay. At this point, if I got anything other than X, I would just stop and say they're not inverses. Okay. What I don't want to see if I'm looking at this on like a test or a quiz is I don't want you to plug it all in and then just literally cross everything out and write X. Okay. You need to show what cancels first, what cancels second. Okay. Because sometimes even though it looks like it canceled, it actually doesn't. Let's look at the other one. This is the opposite. F into G. F into G. Okay, so that looks like 3x plus 1 minus 1 over 3. What happens first? What cancels first? Yep. So I actually don't even need the parentheses in this one because there's nothing that's being like distributed through or anything. So you can look at like this and yeah, the plus 1 and the minus 1 are what's going to go away. So then you're left with 3x over 3. And now you can say, okay, those 3's are going to cancel and we're left with x. Okay, so the question is, are they inverses? If you get x both times, that's your justification. You can just say, yes, they are inverses. And all of that work you did is the proof of that. Okay, again, if you get anything other than x both times, they are not inverses. Questions there? Yeah.
So it's the fact that they're both x's, not the fact that they're both matching.
Right, exactly. Yeah, so if I got like x plus 2 and x plus 2, not inverses.
So
yes.
If you did the first equation and you get anything but x, you just solve.
Yes. Now, if it's a test, I might do the other one too, just to make sure I'm right. But yeah, you could just stop after the first one and say, no, they're not inverses. Okay. Anything else on that one? Proof with composition? Okay. All right. So take a second. You guys try this one with a friend on back of your paper. Go ahead. Determine using composition if we've got inverses. Okay, what do you think? Yes or no?
No.
These are no's. I have work for both of them here for you. You really just only need to do one of them though. If you plug G into F, it looks like this. The only thing you can do here is FOIL it out because you have two terms and it's squared. Cannot distribute that squared through. If the whole thing was under a square root, like if it was the square root of x minus 5 was all underneath, then you would be able to cancel the square and the square root. Okay, but that minus 5 is not underneath the radical. So if you FOIL, which really we don't need to go that far with it, but it would look like this when you FOIL it. Square root of anything times itself is just what's underneath x. That's my first term. Then I'm going to have another negative 5 rad x and another negative 5 rad x, which gives me that negative 10 rad x in the middle. Negative 5 squared, 25, and 5 gives me 30. That's not x. That's what we're looking for. So you could look at it that way. If I plug f into g, I can't do anything at that point I would just stop and say not inverses. So either way, it's not going to simplify like you want it to for these ones. So not inverses from composition. Okay. Any questions on that one? Okay, so now the only other piece of the puzzle that we're left with is how to actually find an inverse. Okay, so how we find an inverse, and if you guys did anything with inverses before, this is probably what you did in Algebra 2. These are the steps we're going to use. First step is we are literally going to get rid of the f of x, put a y there, and then in step 2, switch the x and y. So anywhere there's a y in my equation, I'm going to write x. Anywhere there's an x in my equation, I'm going to write y. Third step, solve for y. Fourth step, put the inverse notation back in. Okay, so the big idea, x and y switch, solve for y, put the notation back in at the end. So we're going to start with this first one. F of x equals negative 2x plus 3. First step, I usually just say f of x is y. I'm just going to cross it out and put a y there. Second step, switch the x and the y. X equals negative 2y plus 3. First two steps are done. They're very easy. Third step is where it's going to look different depending on what kind of equation you have. We need to solve for y. There's not a certain form we're looking for. If you can get y alone, you're good. How do I get y alone? First step. Minus 3, x minus 3 equals negative 2y. Then divide by negative 2. So you can write x minus 3 all over negative 2 if you want. Or you can divide the negative 2 into both terms. It doesn't matter. At the end, instead of a y, we're going to put back in the original function notation. Now this originally was f of x, but notice I left a little space there after the f because that's where we put our inverse notation. Okay. If I wanted to check this, I have several options. Option number 1 is going to be a little longer. I could compose f inverse and f together, like plug one into the other and make sure I get x, like we were just practicing. Option number 2, if you have a graphing calculator, you can just graph both of the functions and look to see if you have that reflection over the diagonal line, like we talked about. That's the faster of the two for sure. Okay. All right, let's try another one. G of x, finding the inverse. Okay, so I'm going to put a y there instead. Okay. And I'm going to switch the x and y. So now it's going to be x equals y over y plus 3. Okay. This gets a little trickier because there's not just one y that I need to solve for. So I'm just going to make the equation a little nicer to start. You can think of this like a proportion, right? That x is over 1. What do we do when we have a proportion? I know you know it. Come on. Cross multiply. So x times y plus 3 equals y if I cross multiply. I'm also going to distribute my x in. xy plus 3x equals y. Okay. Well, I can't get y alone unless the y's are together. So I'm going to move that xy term over. All the y terms are going to go together. And then anything that's not a y term I want on the other side. So there's only one guy I have to move to do that. And then here's the trick. If you can get all the y terms on one side to turn two y's into one y, all you have to do is factor out that y. Okay, it's undistributing it. If I factor y out, what will I be left with in both of those terms? Minus x, and what's left in the first term? A 1. Now that y is multiplied by that parentheses, so how do I get y alone? What's the opposite of multiplication? Divide it. So 3x over 1 minus x is what y is going to be equal to, but then at the end, instead of y, I'm going to put g of x with my inverse notation. Okay. Good? Makes sense? That one's a tricky one, so I want to do that together. Okay. So the other thing that's at the top of this page, this slide, says because I'm switching x's and y's when I create an inverse, all the x's become y's, all the y's become x's. X is my domain and y is my range. Also, my domain and my ranges are going to flip. Now, if you remember when we did domain like a few sections ago, I said, hey, we can't find the range yet unless we have the graph of it. Well, now we can actually calculate the range because we have an inverse. The domain of the original function is the range of the inverse. And the opposite is true. The range of the original function is the domain of the inverse. So if you can find the inverse and you can find its domain, that's the range of the function you started with. Okay, so let's look at that purple one, function f. What is the domain of function f? Are there any restrictions? Square roots, denominators? No. Domain is all real numbers. Let's say I want to know the range of function f. Where I'm going to look is f inverse. Does f inverse have any restrictions? Square roots, variables in the denominator? No. So the range is also all real numbers. And that's a line. Okay, so that's why that's happening. Now, ones like the one on the right are a pretty complicated problem. It's fine. They're like just making sure we're okay in here. All right. For function g, what can x not equal? Not 1, then the top one, the original function. X can't be -3. So when we list the domain, it's everything except -3. We've practiced that before. -infinity to -3, and then -3 to infinity. Okay. Now the range is something that even with a graphing calculator for this, it's pretty hard to figure out because there's like asymptotes on this graph and everything. But you can use G inverse to help you. What can X not be in G inverse? 1. So the range of the original function is everything except 1. -infinity to 1 and 1 to infinity. Okay, so you'll have some math Excel questions that'll ask you both parts. It'll say, find the inverse and then give me the domain and the range of the original function. And hey, if I wanted domain and range of the inverse, I already have those answers. I just switch these. If I want a domain and range of this guy down here, I just switch these. I have those answers already. Okay. All right. So last two problems, we're going to do this one together, and then the last one you guys are going to try on your own. This is just kind of putting all the pieces together now, nothing new. Okay. So we are going to calculate the inverse. We're going to make a sketch of it just so we can see it. And then we're going to name the domain and the range also. I'm going to do the graph first of the original function. Now, this is x squared. We know what that looks like. Yeah, just my parabola. What does the -1 do to it? Moves it down 1. I don't need to make a table for this. If you really want to make a table for this, you can, but you don't need to. Now, remember I said this. You're going to see some stuff like this. Does that mean we're looking at the left or the right side of it? We're looking at the left side of it. The left side because it's x less than 0, okay? Now, you could, if you wanted to make a table, you can just plug in numbers that are smaller than 0, and you can plot these points if you don't know how to graph it, okay? But it's going to look like this. There's my original function, okay? And we restrict it again because it passes the horizontal line test. All right, I graphed the first one. Now let's go ahead and calculate the inverse. What's the first thing I do to calculate the inverse? Switch x and y, and you just got to remember that that h of x means y. So it's going to be x equals y squared minus 1. How do I solve for y? Add 1. And then square root. Now, normally, when we take the square root of something, we put a plus or minus in front of it. I don't want both of them, because if I do both of them, it's not going to pass the vertical line test or the horizontal line test. It's going to be a hot mess. When I switch the x and the y, I'm also switching that guy to a y, which means I only want y's that are less than 0. So that tells me what to use, a plus or a minus. Well, I only want ones that are less than 0. so I want a minus. And that is H inverse. Okay. Now we're going to graph that guy. If you're not sure how to graph it, make a table. Square root functions, think about the first number that you would be allowed to plug in. What would give me a 0 under that square root? That would be the first number I'm allowed to plug in. -1. If I plug -1 in, -1 plus 1 gives me 0, square root of 0, 0, make it -0. Okay. And then anything bigger than that would also work. So I could plug in 0. If you plug in 0, what am I going to get out? -1. If I plug in 1, what am I going to get out? Actually, let's get a prettier number. What about like 3? 3 would be pretty. I would get -2. That's enough to get a graph of it. Okay, so -1, 0, 0, -1, 3, -2, and that is the graph of the inverse. Do you guys see the reflection over the line? A couple of the points are the same. They're just kind of on top of each other there, but you should see your reflection over that line y equals x. Okay, what? I know, they're getting real excited over there. I'm not quite sure what's happening. That's a math class? Yep. Yes. It is. I don't know. I know, we don't have that much fun in here. Okay. Domain and range, just of the original function, is good, of h. Okay. And we have the graph of it, so that should be fairly easy. Domain of x, we were actually given. Its x value is less than or equal to 0. So -infinity to 0. The range of the original function you can find two ways. Again, you can look at the picture, or you can find the domain of the inverse. I'm just going to look at the picture and say, okay, the range is, it looks like it starts at -1, and then it goes up forever. -1 to infinity. If I wanted the domain and range of H inverse, they are just swapped. The domain, you can see in the picture, is -1 to infinity. The range is -infinity all the way up to 0. Okay. And if I didn't have a graph, I could look at the equation and solve for those domains. Set what's underneath my square root greater than or equal to 0 to get those. Okay, so that problem's just kind of like putting all the pieces together. So the last one is yours to try. I'll give you a little bit of time, see if you can find the inverse, graph both the functions, and then find domain and range. Go ahead. What time do we get out of here today? Am I running out of time? Yeah. Actually? Oh, no, wait. 12:11, right? Yeah, we're okay. We can do this last problem. Okay. Go ahead. See what you can do. Let's look at it, and I'll explain a couple of things. So there's a couple of things you have to be careful with here. Were you guys able to get the graph of h, the square root function? So the first number you can plug in that square root is -3, and then anything bigger than it. So you can use this table if you want. I just pick some numbers that would work out nice and pretty. And then the blue graph starts at this point. It's kind of hard to see on there, and goes down forever, okay? And then just from that graph, you can name the domain and range. -3 to infinity is the domain, okay? -3 with a bracket all the way to infinity, and the range is -infinity all the way up to -2. Okay, so all of that I'm just getting from like a table, plotting points, naming the domain and range. Okay, now for the inverse, I flip my x and y. And then this one's a little tricky. First thing I did is move the 2 over. Then, don't forget you still have this negative in front of the square root. So the next thing you need to do is get rid of the negative. You're going to multiply or divide both sides by a negative. I just swapped all my signs to get rid of that negative. Then I squared both sides. It does not matter if you simplify this. There is no specific form we're looking for. So if you want to FOIL it out, great. I don't think you need to, and you're going to make a mistake potentially doing it. So why not just leave it, okay? And then move the 3 over last. And that is your equation for H inverse, okay? Now, to get the domain and range of that, I just took my domain and range and I flipped them from the top there. That's all I had to do. Okay. You can also see here that if I set this greater than or equal to 0, that's where that range is going to come from. Okay, but you can just flip the domain and range up there. In addition, if you weren't sure how to graph this guy, you already had the blue graph. And remember, if we wanted a graph of an inverse, all we had to do was take points and swap them. So if you're not sure how to graph this, or even if you don't want to make another table, don't. Just take points you already have, points in that table, and flip them. And that gives you the other graph. And then you can see the reflection line. Okay? So if you're not sure about graphing, if you can get one, switch and get the other. All right. That's the end of 2.9. Here's the deal. So tonight, you guys should probably be working on 2.8. That's your next deadline. It's due tomorrow night. It's a little longer math Excel, so take tonight to work on that a little bit. Tomorrow, we're going to do like a 15-minute exit ticket on this. And then the rest of the period is going to be yours to work on math Excel. Again, you get that 2.8 math Excel done by tomorrow night. 2.9 math Excel is due next Tuesday night. Okay, so after we get back from the long weekend, we'll still have a whole nother day to complete the 2.9 math Excel then. And those will be the last 2 math Excel. Okay? Questions for me? All right, I'll do salvo and lotto. And then the rest of the period is yours. 25. Oh, somebody's in there. Is that you? Yeah. Okay, give me 1 second. Let me grab Sheena's ticket and then, yeah. Here you go. Well, now you're Yes.
I have a question on that.
Yes.
So I just need use these points.
So I picked -3 because that was what was going to give me 0 underneath. So that's going to be where the square root graph starts. And then I just know that anything bigger than that would also work. Anything smaller, I know would be a negative underneath. You can try like -4 does work. If I plug in -2, it does work. And then I just kind of thought what would give me a 3 square root? Plug in 1, I would take square 4, that would be 3. But you could pick any number you want. That first number is what's really important though, because that's where it starts. You need that part of it. Okay. Did you guys notice too here that whole parabola wasn't graphed? It's only part of the graph. It's restricted because the original one was restricted, which is kind of interesting.